So the folks who aren't able to join us can catch this later. After our introductions, we'll welcome your questions and your conversation. As you listen, feel free to put questions in the chat at any time. And then as we progress in the session, we'll also use the raise hand tool. If you look down at the bottom along the toolbar, you'll see a little smiley face with reactions, and you'll be able to raise your hand like that. So that is another option that we'll be using. If you're not comfortable with the raise hand tool, you can always just put your questions in the chat. If there is any background noise from folks who are listening, I will just mute you. So we'll just be aware that that might happen. Before we jump into our updates, we're going to do brief team introductions. I mentioned that I'm Megan Collins. I'm at the Desert Research Institute. We also have
Keith Jennings. I'm the co-project lead with Megan, and I'm from Linker.
I'm Ben Hatchett. I work at DRI and am a hydrometeorologist and hydroclimatologist on the project.
I'm Nayang Her, and I'm also with Linker.
I'm Sonia Niemanen, and I'm with the Desert Research Institute as well.
we also have Catherine.
Yep. Hi, I'm Catherine Moore Powell, and I'm also with Linker.
So like we said, welcome. We're thrilled to meet you. We're going to start with Nayang Her talking about the scientific motivation for the project. Why are we asking you to send us observations of rain, snow, and mixed precipitation? What is driving the science?
Okay, let me share my screen. Can y'all see it? Okay, wonderful. Well, thank you so much for choosing to spend your evening with us. I'm going to provide you all a quick refresher on why we do this. So I guess we can start off with the question of why. Why am I seeing snow when it's 36 degrees Fahrenheit outside? Why is the rain falling now transitioning into snow? Or why was that not forecasted? So Mountain Rain or Snow is a collaborative effort to answer these questions, to better understand winter weather, whether it is rain, snow, or mixed precipitation. And we do this because weather stations and also satellites just can't do it as well as ground-based observations, as Megan just said. And that's just more so the case in mountainous regions. So we learned from the past seasons that the 0 degrees Celsius or 32 degrees Fahrenheit threshold for the transition between rain and snow is not true for regions across the continental United States. And in fact, through your observations, actually, we found that some regions actually have a threshold as high as 39 degrees Fahrenheit or as low as 33 degrees Fahrenheit. So nailing this threshold between the rain and snow transition is important with predictions for flooding, snow accumulation, and avalanche hazards. And understanding the rain-snow transition is also critical for water budgets and, of course, weather predictions. So not only are these important to predict human life in near real time, but also having a grasp on what these temperatures are for each region helps us with modeling efforts to protect future livelihood. So whenever we receive an observation from you, it only helps us with better understanding the mystery of the rain-snow transition and improve the technologies that predict the precipitation phase. And we are so lucky to have observers like y'all to help us answer all the rain and snow questions, backed up with support from NASA, the University of Nevada, Reno, the Desert Research Institute, and Linker. And over this past year, we had our work published in news articles and an academic journal, and we hope to expand our network to other mountainous regions. So with that, I hope you all got the point that you are involved in a really neat project, and that helps us better predict the rain-snow line, and your input really, really matters. Thank you.
Next up is Keith Jennings, who's project PI, and he's going to explain why your visual reports are irreplaceable for scientists.
Thanks, Megan, and thanks for the intro, Nayoung. One of the things that I communicate with some of my collaborators and peers in the hydrologic sciences community is how irreplaceable human observations are for precipitation phase. So what all of you contribute to this project. This big blob of yellow, orange, blues, and purples is not a scientific Rorschach test. It's really an analysis of how different methods perform when they try to split precipitation into rain, snow, and mixed. And wherever you see the bright yellows, that means that a particular method is quite effective. And wherever you see the darker colors, the blues and the purples, that means it performs quite poorly. On the y-axis, we have a whole bunch of different methods. The individual ones aren't important. It's just to illustrate that we did look at a lot of different ones based on near surface meteorology, machine learning, and also remote sensing products, which could be satellite-based or using modeled reanalysis weather data. And the x-axis is air temperature. So we see those big blobs of yellow when it's cold, so below -5 degrees Celsius. And then we see big blobs of yellow when it's warm, above 10 degrees Celsius. So this is the range of below 25 Fahrenheit and above 50 Fahrenheit. We do a pretty good job at predicting rain versus snow using a lot of these methods. But in between, no matter what sort of method we're using, whether it's based on land surface, weather conditions, machine learning, or remote sensing, they all struggle to predict precipitation phase accurately, rain, snow, or mixed, when the air temperature is right about freezing. And with your help on this project, we've actually come across the reason for that. And these two plots are showing the distribution that you all have provided of rain, snow, and mixed precipitation reports by air temperature on the top plot and wet bulb temperature on the bottom plot. I show both of them because air temperature is the common way of splitting rain and snow, and wet bulb temperature tends to be the most accurate because it incorporates humidity information. And what we see in all cases, that right near freezing, those distributions, those lines for rain, snow, and mixed precipitation overlap quite heavily. So no matter what method we try to use, if we don't have observations of rain, snow, and mixed precipitation, we're always going to come up against this fundamental overlap in their distributions, where if we're trying to use these different methods, they're just not going to be able to tell them apart, because rain, snow, and mixed precipitation fall at air and wet bulb temperatures that are very similar to one another right near freezing. And so we have community observers coming to the rescue. This is a heat map from last year's observations showing where we got the most. And in this case, the brighter colors, the yellows and reds, are where we got the most observations. So we see that in the northeast of the United States. Vermont last year had about 4,000 observations. Same for Colorado, similar number of observations, which was a lot. And then the Sierra Nevada area of California and Nevada came through with about 4,000 to 5,000 observations as well. So it is these observations that make the previous analyses possible. And then moving forward in the coming project years, we're going to be able to work with our partners at NASA on improving some of their model and remote sensing products. So really having tangible results from the science that we do and the observations that you provide.
Third speaker is Ben Hatchett. If you've seen the recent storms on the West Coast in the news, you may have wondered what's behind these phenomena. He's going to unpack this.
Well, thanks, Megan. So our state of Western snowpack so far, partway through water year 2023, throughout much of the West, looks really good. These are a few plots from the United States SNOTEL network, which are weather stations strategically located throughout our mountain regions to help us understand how much snow we have, how that snow is changing, and help us predict, in particular, predict runoff, mainly for the spring and summer seasons, but also during midwinter for flood concerns. And so what we're looking at on the far left is the snow water equivalent, or the amount of water stored in that snowpack if we were to melt it all down. And that tells us the percent of normal to date. And so when you see those dark blue colors or green colors, those are really good things. And so right now, as of today, we have a really amazing start to our water year throughout California, Nevada, Utah, Arizona, and into Colorado and parts of New Mexico, as well as kind of the southern tier of the northern third of the Western US. But as you go further north into Oregon and Washington, Idaho, and Montana, we're not doing phenomenal, but we're doing close to average. So it's a good start, but we're really off to a great, if not amazing start, kind of in the central and southern part of the Western US. And the center plot there uses a similar color scheme to show how much precipitation we've observed in the mountains thus far since the start of the water year in October 1st. And what we see there is, you can tell in the northern parts, we're seeing some whites and getting even into some oranges and not too many reds. So we're below normal precipitation wise. So it's actually been a little bit drier in the northern third of the Western US, but record wet to very above normal wet in the same places that are extremely snowy. And on the right-hand side, what we see is the percent of our total snowpack that we expect. So as of right now, compared to the peak in many stations in California, as well as Nevada, Utah, and Arizona, and even parts of New Mexico, we've already accumulated our peak snowpack amount. Now, that doesn't mean that what we have now will stick around until typically the peak is in March or April, but we really hope it does. But you can see all those orange and red dots mean we still have a ways to go to hit that peak snowpack. So we really are hoping for continued wet conditions throughout much of the parts of the US that have not accumulated as much snow so far. If we move over to the looking US wide, but also kind of thinking about what's been happening in the Northeast, we're in a very interesting situation up there. So these two maps on the left-hand side, the furthest left one shows the percent of normal precipitation. You can see those purple and green areas where it's been extraordinarily wet. Yellow and red and orange areas are where it's been a bit drier than normal. The center plot, or the right-hand side of those two maps, shows our departures from normal temperatures over the past several months. And so you can see the Northwest and northern tier has been cooler than normal. And up in the Northeast, it's actually been a bit warmer than normal. And so as a result of this warmer than normal conditions, but close to, if not above average precipitation, we don't have as much snowpack accumulated there as we would expect. And we call these conditions warm snow drought conditions. This is where we have close to normal or above normal precipitation, but we don't have as much snow. And that can result from rain falling instead of snow, and or dry, warm, or sunny spells that help melt snow during the winter. And so your observations are helping us understand these kinds of events in a place like the Northeast, where we don't have the SNOTEL observations. The figure on the bottom there shows your accumulated observations. The black line shows where people were measuring lots of snow, and then places where not a lot of snow observations were occurring, but we had some rain observations, indicates some of these rain on snow or rain instead of snow conditions that can lead to flooding or can actually reduce our snowpack when we should be accumulating that snowpack. And so rain on snow has been a big, interesting thing for much of the Western US this year. What else does it mean aside from, Nayoung mentioned, flooding or avalanches? Well, when you have snow on trees and then you rain on those trees, that snow can get quite heavy, saturated with rain, breaking off limbs and leading to multi-day power outages, which are not very fun. It also means the snow on your roof will get extremely heavy. And I had to shovel off the roof the other day and there was a lot of snow to move. And as I dug through it, I was able to see all of these different layers that resulted from these various rain on snow events, and a lot of saturated snow. And I even cut a little shark fin to allow the sun to shine through there. And you can see these, I'm not sure if my cursor will show it, but there's those little kind of fingers of snow called preferential flow paths or flow fingers. And these become established through either melting or through rain on snow. And this is how snow or how water moves through the snow and leads to flooding. We get these sort of just preferential flow has established, and then subsequent rain on snow events allow that water to move very quickly through those. While shoveling the roof, I had to dig a snow pit and measure the amount of snow on the roof so I could calculate how much snow I moved in total and how close the roof might have been to collapsing. Doing some calculations, there was over 100,000 pounds of snow or water that got removed from the roof, which came out to be about 42 pounds per square foot, which isn't quite into the full freak out of 60 pounds per square foot, but it was a lot. So if you have a lot of snow on your roof, you might want to get rid of that before we get more rain on snow. And of course, it was raining on the snow while I was doing this, so I was able to send in some observations from that. Thank you.
You heard it here first, folks. Hot tips from a scientist on keeping your roof clear. I love it. That is so practical. So feel free to put some thoughts in the chat. What I'm going to ask you to do, because we're really curious where everyone is located, if you wouldn't mind opening the chat and sharing the nearest mountain range to where you live. I'd love to get a sense of the geographies that are here in the room with us. Mountain ranges or big geologic feature. Feel free to put in water body if there aren't any names.
Chat's disabled.
Oh, let me. Thank you.
But cascades, anyways.
Thank you. Ooh, hold on. That's never happened before. Okay, try it now. Thank you for pointing that out. Awesome. Cool. Cool. One of the really cool, I'm just seeing, we've got Colorado, we've got the Sierra Nevada, we've got the Rocky Mountains, Sierra Nevada, we've got Cascades, we've got the Northeast, we've got some from the Tetons. This is awesome. One of the areas of work that came out of the project this year was using your observations from last winter season. Keith and Nayoung created what we call snowfall probability curves, or they calculated the probability of snowfall at different temperatures across different regions, and they were able to compare. And I'm curious, Keith and Nayoung, if looking at the regions that are located here, if you want to share any insights comparing those regions kind of based on the folks who are in the room. Any cool insights that you learned from that work, knowing that the probability of snowfall at different temperatures is not the same region by region. At least that's what we found last year. Any insights from that?
Well, I'm just going to say I'm glad to see there's one more person from the Green Mountains with whom I can commiserate on our terrible snow season that not only we've been experiencing, but Ben had to put in graph form for us to look at. And while he was doing that, I brought up the Mount Mansfield snow stake, which is one of, I don't want to misspeak, but I think it's one of the only long-term snow measuring sites that have data publicly available on the East Coast. And it's one of the, I believe, 5 worst winters as of this date. And so here in New England, we are incredibly sensitive to temperature. This goes for the Cascades as well. We're right on that fringe of, if a storm comes in warm, then we're right at that threshold where what could have been a 2-foot snowstorm turns easily into 3 inches of rain. And I saw that Paul just noted in the chat, the wind direction in temperature. So where our storms come from is pretty important, and they have different properties depending on where they're coming from. Whereas in Colorado, really it's not temperature that matters, it's precipitation. So if you're in the high Rockies, you're not necessarily caring if it's a few degrees warmer than normal because it is so cold. And most of the Rockies, 90 to 100% of your winter precipitation is going to be snow. So temperature doesn't make as big of a difference there, whereas here in Vermont, ratchet it up 4 to 5 degrees Fahrenheit, and then all of a sudden we're above normal precipitation, but half of our annual snowpack, which is pretty wild. At least for me, that's what I've been experiencing this winter. I don't know if Nayoung wanted to follow up with anything else besides just my tales of woe in New England.
No, that was amazing.
So another thing that I've been seeing in the news this year is every season it seems like there's a new weather-related term. We've had this year we saw this term parade of storms, and it happened to be that we had a series of atmospheric rivers that hit the West Coast. And I'm curious if, we kind of hear the shorthand version that there are a plume of very wet weather that comes out of the tropics and hits the West Coast. Is there anything, Ben, that you want to unpack for us about what exactly atmospheric rivers are and why they matter so much for this type of work?
Sure. And I have a slide for that, just for you all. So you've probably heard the term atmospheric river either from friends or in the news, or maybe seen a picture of it or a schematic of it. And really, we have them to thank for our awesome start to the Western snowpack. And we also can blame them for extreme flooding, or you can kind of blame them for anything. If it's snowing a lot and raining too much, blame them. If it hasn't done enough and you're in drought, well, you can also blame the lack of atmospheric rivers. So from satellite, which is how we originally started to visualize these, but now we can model them very well and we can observe them other ways. But if we look from satellite, these are what they look like. They're these very long filamentary plumes of concentrated water vapor that get essentially pulled up from the tropics and wrapped into the developing storms. This storm here is what turned into the bomb cyclone that you may have heard all about. And what is currently impacting California at this time, this was right around New Year's, was this very, very warm event that caused a lot of rain on snow, saturated the snowpack, made the roof probably 10 times heavier than it was beforehand. And so these types of storms are extremely important for many places in the mid-latitudes, but also in the polar regions as well. They have lots of water vapor associated with them. They lead to extreme precipitation, whether that's rainfall or snowfall, and they really make or break our season in a lot of cases because they contribute such a large percentage and really drive the variance. If we get 3 or 4 of these, we have maybe a drier year. If we have 5 or 6, we have an average year. And if we have 8 or 10, we're worrying about flooding and things like that. They are also typically associated with rain on snow because they tend to have so much of this warm subtropical and tropical moisture associated with them. And so this year, we haven't really seen any crazy rain on snow driven flooding yet, but we're ready. The soils are saturated, the snowpack is wet, our reservoirs are filling up, so we're like right there. And really, this has probably been the best year to see consistent high impact or soon to be high impact rain on snow in the Sierra Nevada since probably at least 2017. And this is really cool because this project and all of you are helping us document it and understand what's going on, what are the temperatures and relative humidities and weather conditions associated with this, and when are these things happening. And so at the bottom, you can again see another one of these cumulative observation plots. And we've had a number of these events, and you can see them when we really climb up in terms of a lot of rain observations. Sometimes we'll still be seeing snow at the higher elevations, but there's been a few times this year where we've seen lots of rain all the way up to 8,000 to 9,000 feet before that finally turned to snow. So Next time you hear the term atmospheric river, you can draw this really nice little plume of water out of the tropics coming towards wherever you are. And then there's the low pressure on the upper left-hand side of that. And then you could draw a big H for high pressure on the other side.
Great, I love it. I'm noticing some comments in the chat about like the difference between the leeward and the windward side of the mountain in terms of snowfall. We've got hydrologists in the room and we've got climatologists in the room. I'm curious, a couple of different perspectives on rain shadow effect and snowfall or watersheds. Any comments, anything you've learned with respect to this project for that? I'm going to drop another term, but like how storms are affected by orographic lift, and anything related to this project. And if you do want a sticker, click the link that Sonia just put in the chat. We will send you one for free. It's a little cool nylon decal.
Yeah, one of the things we've used only from the Sierra Nevada so far, we've used the citizen science observations for a couple of years to estimate the rain snowline elevation. And we can do that because there are certain big storm events where we get enough observations from community observers, upwards of 100, I think, probably on some of the bigger days. But then I guess the past few years, we've probably had some storm events that give us 100 to 200 observations, but these were from earlier in the project. But anyways, we use these days with lots of observations, and when there is rain and snow across the study domain. So it could be, somebody could be reporting snow up at 8,000 feet, and then somebody down in Reno or Carson is reporting rain at 4,000 feet. And there might be a mix of observations in between. So we can bin all these reports by elevation and calculate the snowfall probability per elevation bin over the course of a day. And then on some of these days when we have enough reports, we can plot this really nice positive linear relationship. So it looks like a straight line going up the Sierra Nevada, where as you increase in elevation, your probability of snow increases. And then we can estimate a rain snow line based on where that probability crosses 50%. And we've also compared it to some data that Ben works with, and that's from a freezing level radar located on the other side of the Sierra. And in general, our data are like 150 meters or so higher in terms of the rain snow line estimate. But it's just another cool way that we can use these volunteer reports that you all submit in order to get a better handle on snow and snow processes and where it's raining and where it's snowing, that we really didn't have any sort of clue before. And then I guess I'll add another bit into the mix. I've looked at similar types of data for Vermont, and we don't quite have the orography to make those types of plots and relationships. So it's the Sierra is a really great study area where you have so much topographic relief in a very short distance, and a lot of people, which lends itself well to this sort of data collection and analysis.
Yeah, and I'll just add to what Keith was mentioning, that these freezing level radars that we have on the western side of the Sierra Nevada are great tools, but they only work on the western side. And we, until now, did not have very many observations or ways to get observations of where that rain snow transition is on the eastern side of the Sierra Nevada until we had human observers. And so this is really exciting to be able to put together where that rain snow line is on either side of the Sierra Nevada, because we have different processes at work. When you drive up from the west side up and over the mountain, you're on a slightly moister side of the mountain. And so the air temperature decreases with height at a slower rate than it does on the eastern side. So when you go from top of Mount Rose Summit down into Reno or Carson, it's going to get a lot warmer more quickly on that side. And that's because you're under a different, what we call lapse rate. And the same process applies even during precipitation events. And so we think that's one reason why the snow line characteristically is a little bit higher on the eastern side of the range compared to the western side. And humidity plays into that as well. And there's a bunch of other kind of during storm processes of interest too. But this data is going to be really important to be able to better understand how all these things work. Because before we were just kind of making estimates based on temperature thresholds, which we've seen don't really work all that well all the time. And so this is kind of very invaluable data to be able to understand how these processes are changing through time, through space, different storms, things like that. So it's really cool to be building this database up.
We look at the forecast, for example, what National Weather Service puts out. We often see them estimate the elevation of snow, and I'm guessing that this is similar across different regions, right? We'll see rain turn to snow at 2,000 feet or 4,000 feet. Is it difficult to predict where that snow line will take place simply because of the technology challenges that Keith outlined before, or are there other reasons? Are there storm-related reasons why it's just hard to predict for meteorologists? And if you want to link it back to, again, what we're doing, feel free or not.
And Megan, I did see a question in the chat.
Thank
So
you.
I can answer that. And then I've got questions to ask as well. But for those of you who are here joining us today and have any questions, whether it's about the data, the project, us as people, what type of dog I have, or it is Ask Me Anything. We might not answer everything, but go ahead and ask what you have. And so, Joni, I will answer your question. We do want reports from all over the nation. I'll let Megan expand on this point in a second. We found that engagement at a local level is really important. So we're only able to focus on a few regions at a time, but reports from everywhere do go into our database. And we're working on a processing workflow this year that will allow us to ingest and incorporate meteorological data, remote sensing data from all across the country and do some really neat modeling and analysis with the data we do get. And so I know Megan has worked a lot on the human engagement side of things, so I'll let her take over and answering how the engagement process works.
Briefly, if you haven't checked out our website, you can go to rainersnow.org, and on the homepage, you'll see this little table that outlines all of the different regions that are part of the project right now. You probably signed up for the project by finding your regional keyword and texting it to our project number. We started with just one keyword in the Sierra Nevada. Then last winter we had 4, and we've again doubled it. So Sonia and Nayang and Catherine and I and Ben and Keith, everyone contributes to monitoring the weather in these different regions so that we can send you accurate alerts that are relevant to you, that also explain why those particular storms are of interest to the science. So if you know folks or groups, ski groups or other outdoor environmental recreation groups that you think would be interested in participating in any of these regions, please feel free to let us know. As you're probably aware, but maybe not, you can always reply directly to those texts that come out. You reach a real person. I love hearing from you. I love hearing how much snow accumulates. I love hearing what's going on, or if you have questions, I can answer them, either technology troubleshooting, or we can field science questions across the whole team. So the short answer is yes. From anywhere in the country, we send alerts to these regions, but if you are located somewhere else and want to participate, there is absolutely no stopping you. So would it be possible to have more options to report, like mist, sleet, etc.? This is a great question that we actually get a lot. The reason that we have the specific options that we do is because they correspond to the NASA satellite observations that are being taken, those particular categories in the technology that we're trying to improve. So you may be aware of other projects that have a greater number of precipitation types. That's because they feed into different weather monitoring technologies. Anyone want to build on that response?
Yeah, I can give, it may be sort of an unsatisfying answer, but it is a real one. And so I commented in the chat about CocoRAS. So they're one of our community science partners, and they have long-term, short-term, all sorts of monitoring across the country. So if you're looking to report precipitation depths, snow depths, temperature, they're the ones to do it with, and they're great. But the different types. So we started as a very small project in the Sierra, and by trade, I am a hydrologic modeler, which means I use computers to try to understand and simulate the natural system for flood prediction, water resources forecasting, what have you. And the models that we use, in many ways, are very intelligent, but then there are a few processes that they are quite dumb at. And one of those processes is determining rain versus snow. That figure I showed before, when it's cold, sure, no problem. The models can use air temperature to split precipitation very clearly into snow. And when it's warm, it's very clearly rain. But at those air temperatures near freezing, they can get 40, 50, 60, even 70% of precipitation phase simulations incorrect. So they think it's snowing when it's raining or raining when it's snowing. Mixed is just a whole other can of worms. I was gonna say bag of cats, but I knew that wasn't the expression. So these land surface models, hydrologic models, water resources models are typically only concerned with rain and snow because they typically sleet, hail, etc. are such a tiny fraction of the annual water budget that when we're trying to represent them in long-term or even forecast simulations, they don't actually tend to matter that much. So most models, and even some weather models, some climate models, and remote sensing products only consider solid versus liquid precipitation. So that's essentially our mission, is solid versus liquid precipitation. And now at this point, you might be thinking, isn't hail solid precipitation? Yes, it is. Hail is very much frozen, but it forms from a wildly different process than any of the precipitation types that we're concerned with. And it's more of a summer phenomenon where we are primarily a fall, winter, spring project, which sounds a little silly when I say it out loud, but these are, particularly in the Western United States, the most hydrologically important seasons and months that set the stage for water resources for the rest of the year. So rain and snow are the most important. We might consider more phases at some point, but even I, as a seasoned observer, can struggle to differentiate graupel from sleet. And so the more splitting you do, the more you get into quality concerns. Is this actually a report of graupel, or is it sleet? Or this person said it was slushy out, or whatever it happens to be. So if we keep it simple like we have done, we find that our observations are of generally high quality. Yeah, so that's the answer. Really, we're trying to keep it simple.
Hey, Keith, I'll go ahead and play devil's advocate here and expand on that. I think as the project does start to move into more areas and less mountainy areas, and I'm thinking in particular, the Great Lakes is a good example. And I'm not talking about the lake effect areas on the east side, but more on the western side. I could see where they may want to have more precipitation phases included in this. And especially seeing as how I used to live in Chicago, sleet was very much a predominant form that we got during the winter. Could that be one of the aspects as this project continues to grow and expand into other areas?
Possibly, but again, we're really focused on the large scale water resources component, and starting in the Western United States and expanding to New England. It's really those two phases plus mix that are the most important.
Great question. Jen's got a comment when it has been raining or snowing all day, how often should we be reporting an observation? Usually just report when it starts. And then there's a second part of the question, which we'll talk about in a minute. We recommend that, and we know you have busy lives. We always take observations in real time. So if you notice that it's precipitating outside, send us an observation. If you can remember to send us observations at 30-minute intervals, that is ideal. And I think you heard a couple of different examples of storm events and data that you showed that really showed the value of that kind of, we call it longitudinal, or those snapshots in time. No fewer than 15, but if it does change phase, if you notice, like sometimes it'll go from snow to mixed to rain or the other direction in, the course of 10 minutes, definitely send us observations in that, in a lower frequency than 30 minutes. Was there somebody who wanted to add anything? Why?
I would. It's actually a tip I stole from one of our community observers last year who sent us an email about this. He's not on the call today, which is too bad because I would give him credit otherwise. But he said when it's really cranking out there and he's in the Sierra where it can go from rain to snow to rain to snow multiple times in a day, he sets a timer for 15 to 30 minutes. And so I've started doing that at home when we get interesting storm events. And it actually accomplishes for me two things. One, it gets me submitting more reports, but then two, it also forces me to stop looking at my computer for at least 30 seconds. Granted, I then look at my phone, but at least in theory, it gets me from looking at my computer and looking outside and reconnecting to the natural world for at least a few seconds. So if you want to do that, that's great. These sort of high frequency observations during interesting storm events are really, really useful because they pick up patterns. So the reports from community observers pick up patterns that just are not capturable by satellites, by weather products, and by models. So the more observations, the better. That's sort of my take home point at this time.
There's a second half to Jen's question, which builds on, now this sounds like a simple question. How do you know when it stops in our area of reporting, when it stops precipitating? But it gives us a chance to kind of dive into some of the current weather monitoring technologies. And I want to preface what our scientists are going to say by saying that there are a lot of very good weather monitoring technologies. We're trying to make them better. So these are existing technologies that do a good to great job, and we want to make it a great to excellent job. And I'll kind of pass it off. What existing technologies are out there to monitor our weather, and why does our project not need to know when it stops, or why are we not asking people to share when it stops raining or snowing?
I thought Ben would answer, but it looks like he's deep in thought. So I'll throw in the first idea, and then he or someone else can take over. But a good way for us to know it stopped precipitating is that we stop getting observations. So the absence is sort of the evidence in that case. The second, well, there is a caveat to that, in that most people report observations, myself included, when they're awake and not when they're sleeping. So probably 95% of our observations are between 9 a.m. and 9 p.m. So there is definitely an exception to that. But the other part is that precipitation occurring, those technologies are much more mature than precipitation phase technologies, if that makes any sense. So rain gauges are actually quite good at saying, oh, it's precipitating now, or it's not precipitating now. Again, there are exceptions, but maybe Ben can throw in a few more details from the hydromet side that I don't have.
Yeah, so I think the absence of your observations, if you kind of are consistently observing during a storm and then it stops and you stop, that's helpful for us, because then we know, okay, we're not seeing any more observations in this one area, but maybe we are in this other area. And so we can use either, like Keith was mentioning, precipitation gauge observations, or in some places where we have good radar coverage, radar is another way that we know, is it getting to be kind of patchy, scattered precipitation, it's in this part of town, not that part of town. Oh, I live up on the mountainside and it tends to linger up there a little bit longer. So I guess as long as it's precipitating, any measurement at really any frequency is good, especially if it is kind of varying. Like some of these storms at 6,200 feet, it would be raining and then snowing and then definitely a mix and then snowing and then raining. And it's like every 20 seconds you could be taking an observation, which would be really cool. So we can kind of see how things vary in there. But yeah, also to build off what Keith was mentioning, we're really good at observing some phase of precipitation, whether it's rain or snow or mixed, but discriminating what kind it is, there's almost no substitute thus far for either cameras or really expensive vertical radars that are cost on the order of $80,000 for one point and one location. So it's much more cost effective to have well distributed observations throughout. And so if it's changing phase, those observations are great. As soon as it stops, you can stop as well. I mean, I suppose a none could be an interesting thing to add, because zeros in precipitation measurement are always really good to say, no, it was a dry day, it did not do anything there. But yeah, I think it's as high frequency as you see fit. And if you really want bonus points, maybe Megan can run a contest that'll have you, who can submit the most observations overnight one night during a really cool storm.
Have a nuit blanche. Play on words. Have a white night during a snowstorm.
I remember when I was a kid, my favorite thing was up on Donner Summit at 7,000 feet. So kind of the higher end of the rain snow line. I would always wake up when I wouldn't hear the precipitation hitting the roof, because that meant it was snowing. And then you look outside and it was like Christmas every day, because I guess everything in white. Oh, this is great.
Love it. That's awesome. Some of what you were saying is kind of speaking to Joni's comment about in December there in Seattle, they had snow, rain, hail, and sleet all in one day. So totally tracking all that difference is really super useful. And I'm going to go to Paul's question next. He asks, is super wet snow coming down in sheets that are just barely flakes? Should I categorize that as snow? It's not quite melted, but almost. And this, I think this speaks to the challenge that everyone has been talking to tonight about why these technologies really struggle. Even our human eyes can sometimes struggle. And what we're asking you to do is take something that exists on a continuum, right? Rain to mix to snow, it exists on a continuum. And we're asking you to put it in these neat little categories when it might not be that simple. I think getting different perspectives on this, maybe each team member can weigh in on how they recognize mixed. For me, if it's not a clear rain, not a clear snow, if I have to look at it twice, it looks like crystallizing water or melting snow, I'm going to put it in the mixed category. I'm curious how others view it and describe it.
I'm with you, Megan. My first instinct was I would call that mixed. So.
Yeah, and I kind of think if it's falling very fast, but it sort of makes me think snow, but it's falling really fast, it's not accumulating on the ground, it's, you can use the like windshield splatter, like, do I see little ice crystals left? Those are all kinds of things I think of mixed. But if it's more slowly falling, even if it at high intensity, that's where it's like, okay, this is definitely snow. But if it's falling very quickly, that's one good way. And that's actually how some of these vertically oriented radars identify the rain snow transition in their algorithm, is they calculate that fall speed to see how fast things are falling. And if you have things falling very quickly and then also changing the dielectric constant of water, which happens when water goes from frozen to liquid. Those are the two key things that are used in those kinds of algorithms.
Yeah, I always we get a lot of those sort of tweener storms here in Vermont. So I try to look for the liquid. If I can find the liquid, or if it's really on the fringe, I put it as mixed. But yeah, like Megan said, that fine line and breaking a continuum up into categories can be really tricky. So I will just throw a little bonus tidbit on top of this. Is this project has really highlighted how little we in the hydrologic sciences know about mixed phase precipitation. And what this study is showing is that even instantaneous observations like the ones that you all are reporting have a pretty high proportion of mixed. Season to season, it tends to be about 15%. And one of the primary satellite monitoring system for precipitation is called the Global Precipitation Measurement Mission. And one of the products that they present doesn't even consider mixed precipitation. It just says, here's the probability of liquid precipitation. If it's at a certain level, it's snow. And if it's at a certain level, it's rain. But a value of 50% probability does not mean mixed. It just means that it's as likely to be snow as it is to be rain. It doesn't consider this mixed precipitation. And so this project is sort of highlighting to us that there's really a lot more we can investigate on mixed precipitation. So there might be more coming from us in the next few years about mixed precipitation investigations.
Great. We've got a quick question to answer and then one that might be a little more in-depth. What are the months in which you want us to send reports? You can send reports all year long. Know that the focus of the rain to snow transition is often the winter, but I'm sure that some of you live in areas where it could snow any of the 12 months. We send alerts, we send those weather alerts by text message between November and the end of April. So know that you won't get alerts in July, but we had a lot of, especially in Colorado, we had a lot of observers sending us observations year round. And I heard a couple of comments on just how valuable it was to know when did, like Ben had said earlier, or earlier in the week offline, it's really nice to know when the snow is stopping, when the snow season stops year over year. Any other comments on kind of the annual cycle before I jump to freezing rain question?
I would just say shout out to Michael in the 10-mile range where summer is about 2 months of the year. So those might actually be the most interesting months in terms of this project. Whereas Vermont, once end of April hits, I mean, we're not getting any snow anymore, but in the 10-mile range, it could snow on you every month of the year. So definitely observations every month of the year, particularly the ones that fall at temperatures close to that rain snow transition. But again, going back to my adage, more observations, the better.
Sweet. So Adriana brings up rain turning into ice on the ground, or this phenomenon of freezing rain. And this is a sincere question. We have put out, this project has put out several kind of explanations unpacking why we see snow above freezing. But I actually do not know, why is it that we can see rain falling below the freezing point? What's going on in the atmosphere that drives that phenomenon? We know how much damage it can cause, tree limbs to break, and it can be a safety issue. Why do we see that? What's going on?
So that's a really kind of bizarre situation that doesn't set up all too often in more southerly places, but kind of like what happened in Seattle and occasionally happens in Portland, and then also more frequently in the Northeast in particular, is where you have a warmer layer of air at the surface or somewhere near the surface, and then right at the very surface, it is actually below freezing. And so precipitation moves into the region. It may be falling as either rain or snow, But once it gets to the very nearest part of the surface where it is below freezing, it will freeze on contact. And that's what creates this total catastrophe of roads and trees and power lines. And, you can't even walk out your house because you're going to slip and fall down the street and end up in the ocean. And so it's a really dangerous and difficult situation that can occur. And it's really interesting to be able to get these observations of it. In the Reno and Tahoe region, it happens occasionally when we have cold air trapped in the valleys. So when it's very inverted conditions, it's cold and maybe cloudy for a week in the valleys. And then a storm moves in, but that storm is not windy enough to scour out and mix out that inversion. And so it can actually be raining at 6,000 and 7,000 feet. And that rain can then either turn into freezing rain in the valley, or sometimes if it's kind of mixed phase precipitating at the lake, it will kind of refreeze into sort of a weirder, chunkier type of frozen precipitation. So you may be seeing mixed or rain up at the lake and freezing rain type, or sorry, snow or kind of mixed to snow type precipitation at lower elevations. But the freezing rain events are not too often, thankfully, on the West Coast, but they are really disastrous when they do happen. And on the East Coast, they're probably once a year. I don't know. Some of Keith can probably comment better on how commonly those happen, but they definitely make a mess of things for days on end in some cases.
Yeah, so while Ben was talking, I brought up some of the data that we collected last season. So these curves are all created from data that you all have submitted. Air temperature again on the x-axis where it likes to hang out. And then the y-axis is showing snowfall probability. So in each of these three locations, the Northeastern Highlands, which is approximately Vermont where I am, the Sierra Nevada of Nevada and California, and the Southern Rockies primarily in Colorado, at least from the data we collected. So the Southern Rockies and the Sierra are pretty similar in that when it's below freezing, when you get close to zero, it tends to tail off a little bit, but these are mostly snow events. But if you switch to the Northeastern Highlands in this green trace, in this green curve, we see that essentially once you start moving from the coldest air temperatures to warmer air temperatures, there is a large proportion of precipitation falling below zero that is liquid or mixed. So it has some liquid component. And I wouldn't put a hard quantification on it, but where I am, we probably get 5 to 10 below freezing rain events each year. And then probably half of those are what I would call freezing rain, where the rain actually freezes once it hits the land surface, which can be quite dangerous. So I'm on a dirt road with curves, and just the other morning we had a bunch of cars off the road that we had to help people with because the road was just a sheet of ice. So mountain rain or snow is helping us figure out those processes and hopefully better represent them. So going to get some real good out of these data that you all provide.
Fantastic. We're gonna wrap up to put a punctuation mark in the end of this session. I just want to note a couple other comments that have been going on. I really appreciate the feedback. We heard some really great input tonight in the chat. Thank you so much for providing that feedback. We are always interested in hearing your comments and experiences, so thank you for sharing that. If you haven't already heard about the photo contest, Sonia's got a link in the chat here for sharing your kind of on the ground experiences of these interesting weather events. We've got a few different categories. We'll be picking winners in each category. Submit your photos. The due date's just about a month away, so you've got lots of time to collect those photos. We're excited to see them. I'm glad Jody's excited to see them. We're excited to share them and kind of see the project through your eyes, and also share our impressions as folks who work with the science. So thank you so much. I have also seen a couple of shout outs to Cocoa Rods. They are an amazing program. If you haven't heard of it, it's the community collaboration of Rain, Snow, and Hail. And if you are into weather and you want to know how much is falling, you can get a rain gauge. There's a couple links in there. So I will hang on just another couple minutes if people have specific questions about observing, but we'll stop the recording and we'll say goodnight. Thank you so much for staying up. I know some of you stayed up late. Others are probably eager to get dinner. We appreciate everything you do. It's so nice to meet you. And we look forward to continuing to collaborate in the future. Thank you.